So the two-dimensional wave equation, and we will see how this goes. So first off, we need to state the problem, and the PDE that we have is UTT equals C squared UXX plus UYY. So now we have a time variable and two space variables. We need, as always, the domains. And so here, X varies between 0 and A, Y varies between 0 and B, and T is greater than 0. We need boundary conditions. And what we want is that the boundary is, let's see, A, Y, T is fixed. That should be X 0T equals 0 and U of X B T equals 0. Okay, so those are boundary conditions. If we set X equal to A, we should get 0. If we set X equal to 0, we should get 0. Y equal to 0, Y equal to B. That should also give us 0. So boundary conditions, oh, and then we need initial conditions. U of X comma Y comma T equals 0 is some function xy, and then UT of X, Y at 0 is some function G of XY. Okay, so what's the idea when we're thinking about the two-dimensional wave equation? What's the thing that we should be thinking of? And in this case, think of a square drum, right? A drum that's top is a nice rectangle. X goes from 0 to A. Y goes from 0 to B. And the edges here are fixed, they're nailed down, that's our boundary conditions. And the initial conditions, right, this is our initial position, is F, G of XY is the initial velocity, and U is the shape of the drum after you hit it, right? So we have a square drum, you can pull it, pluck it, move it, get it started, and then we want to know what does it look like as it goes. So how do we go about solving this? Well, same kind of construction as before. We'll separate the variables and find the ordinary differential equations with boundary conditions. So we'll assume that U, I need to put my cursor down there. U of X, Y, T is some function of X times some function of Y times some function of T. Okay, and then you plug that into the equation, the PDE itself. And we get X, Y, and then second derivative of T equals C squared, second derivative of X times YT plus X second derivative of Y times T. Okay, and then we'll divide by C squared XYT. So divide both sides, and that gives us second derivative of T over C squared T equals second derivative of X over X plus second derivative of Y over Y. So as what usually happens, the right-hand side now depends only on xy. Little x, little y. Left-hand side depends only on t. We have two functions of different variables that are equal to each other, no matter what the input variables are. Then the only way that can happen is both sides are equal to some constant, which we'll call k1. That's supposed to be a y. There we go. So we can get an ordinary differential equation from t, or t from this. Take this part, multiply both sides by c squared t, and collect all your terms on one side. D squared t dt squared equals minus k1 c squared t equals 0. Okay, so that gives me an ODE for t. We'll put a little box around that because now we know what that is. And then we also get k1 equals, k1 equals x over x plus y over y. But we now have two functions, one of which depends on x, one of which depends on y, and adding them together gives me a constant. So I'll separate this. We'll put the y terms over with the k1. And now we have the same deal, right? The left-hand side depends only on y. The right-hand side depends on x. So we get another separation variable, k1 minus y equals k2 equals x over x. So we can get ordinary differential equations out of that. We get an ODE for x, which again, you take this thing and multiply both sides by x and gather the terms on one side. Here's our ODE for x. And then it also gives us an ODE for y. Right, we have this thing. So subtract k2 from both sides, add the y over y to both sides, multiply through by y, and then gather all your terms on one side, and you'll end up with d squared y dt squared minus k1 minus k2 times y equals 0. And so there's our ODEs. And I should throw in here that we want x of 0 to be equal to a. I'm sorry, let me rewrite that again. X of 0 should be equal to 0. X of a should be equal to 0. And y of 0 should be equal to 0. Y of b should be equal to 0 because those are our boundary conditions. So now in solving for the ODEs, we should be able to get quantization of the separation constants. We should be able to evaluate what K1 and K2 are, at least find some restrictions on them. So to solve these ODEs, you've seen these before. The 2D heat equation has the same ODE for x. So that tells me that x sub n is going to be equal to sine. I'm not going to do the derivation again, n pi a over x. And we get y sub n equal to sine m y sub m pi over b y, and we evaluate k1 to be minus n pi over a squared plus m pi over b squared. Point. Okay. So, and K2 is n pi over a quantity squared, but we're not going to need that again, so we'll just ignore it. The ODE for time, however, is different from in the heat equation because here we have a second ordered ODE for T. And that becomes d squared T dt squared plus, well, it's plus K1, which is this whole thing. N pi over a is actually minus K1. So that's why the minus signs went away. M pi over b squared, T equals 0. And so this equation, we know what this is. This is some positive number. And so we know what the solution to these kinds of things is going to look like. T as a function of T is going to be equal to some, wait, I know the undo button works here. Let me undo this a little bit because I need to include the indices. T will depend on m and n because it's got an m and n here in this constant, and that's going to be some constant, which we'll call AMN, cosine of what I'll call lambda mn T plus BMN, comma, n sine lambda sub mn T. And for brevity's sake, we'll call that thing, that whole coefficient there, lambda m sub n quantity squared, and then that gives us this equation for T. Great, so what are the solutions we have here? The normal modes are x sub n equals sine n pi over ax, y sub n equals sine m pi over a y, and then T, that's an m, depends on both m and n, and that's some constant cosine lambda m n T plus b m comma n sine lambda m n T. So the normal modes depend on both n and m, and they are, as defined above, just x times y times t, which are those things. And then the series solution, so what's u? That's going to be the sum of these things. And so it's going to be a double sum, n equals 1 to infinity, sum m equals 1 to infinity of u n m x y t. That's going to be sum n equals 1 to infinity, sum of m equals 1 to infinity of sine n pi over ax times sine m pi over b y, and this here should be a b, I just noticed that was incorrect, times a m comma n cosine lambda m n t plus b m n sine lambda m n t. And lambda mn is given by this thing. Right, so there's the solutions. Now we want to be able to find out what the coefficients amn and bmn are. So we know at t equals 0, u of x, y, 0 is my initial position, which we're calling f of x, y. And that's the double sum n equals 1 to infinity, m equals 1 to infinity. Now, if we set t equal to 0, these terms, the sine terms, and I need another parentheses there, will be just 0. So we get sine n pi over a x sine, m pi over by times the coefficient that we're after, cosine. Oh, nope, no cosine. If we set t equal to 0, this just becomes 1. So there's our equation, and we want to figure out what the amn are. So we can rewrite this a little bit. We set, just to make our notation a little bit easier, phi mn of xy to be equal to sine n pi over ax times sine m pi over by. So what we have is, oh, and we set the inner product of two functions, f of g, to be the integral from 0 to a, integral from 0 to b of f, and f has to be a function of x and y. G is a function of x and y, dy dx. So there's our inner product. And then what do we get? If m prime n prime does not equal mn, then we have our nice orthogonality conditions. Two different functions of this form are orthogonal with this inner product. And if we take a inner product of a function with itself, we get AB over 4. Good, so what does that mean we can do? We have f of xy is now given as a sum n equals 1 to infinity, sum m equals 1 to infinity of a m comma n, b of m comma n. So if we want, say, aij, take the inner product of this with respect to phi ij, and that's going to be, well, the inner product of this double sum with that. By linearity of the inner product, we can move the inner product m equals 1 to infinity inside of the sum, and you get this thing. So phi ij is a particular one, and we want to know what's the inner product of this. What do we get? Well, this is the inner product of this on the left. So all of these inner products are 0 unless the two things actually match. So this is going to be Aij times AB over 4, because that's what phi ij comma phi ij is. So AI comma j is 4 f comma phi ij all over AB n pi over ax sine, I wonder if I have enough room, m pi over b y times dy dx. And so that gives us what the coefficient is. So to find, need to insert a page so I have enough space to do all this stuff on. Oh, where did all my stuff go? I'm not quite sure what happened there, but okay. So to find bi comma j, this is ut of x, y, 0 equals g of x comma y. But if we take our function and differentiate it, right, way up here at the top, I don't know where this page came from. Here's u, and since I have some space here, the derivative is the sum n equals 1 to infinity, sum m equals 1 to infinity of sine n pi over ax sine m pi over by times, now when I differentiate this, I will get minus lambda m n t times am n times sine of lambda m n t, because I have to differentiate this with respect to t, plus lambda m comma n b m comma n cosine of lambda m comma n t. So when I set t equal to 0, the sine terms will be set to 0, so those will go away, and I'll just be left with the cosine terms. But cosine of 0 is equal to 1, so we get lambda mn times bmn. So coming down here to the end, b m comma n times lambda m n b m n. So, and a similar process to this above gives you bij equal to 4 ab lambda ij double integral 0 to a 0 to b g of xy, because that's our initial velocity, sine n pi over ax sine n pi over by dy dx. So similar procedure that we've seen before. Separate the variables, get the boundary conditions, separate the variables, get ODEs with boundary conditions. The boundary conditions tell you what you get as your normal modes, because they rule out some solutions and force K1 and K2 to be particular things. In this case, the integers n and m. Solve the equation for t, multiply all the normal modes together, and that gives, and add them up, and that gives you the solution to find the coefficients use the orthogonality of the normal modes to peel off the conditions one by one.